Ramanujan for G is now available on the Google Play Store. Try it out for free.
Hi students. So today we are looking at alternating currents. So this is we've been going through the material and alternating currents, and this is maybe the third, fourth class here. So you should have seen the previous classes. We started with AC circuits and we introduced AC power. So now we are taking a step into what is called LCR, which is circuits that involve alternating currents and the use of these in actual circuitry, which where there are AC sources involved and they look to transform signals. Now, before I go into that, let me reintroduce our two products. Sushruta for NEET is our flagship for NEET students. It is you get a chance at using the best NEET application in the market for free on any Android cell phone. You just go to play.google.com and look for com.jnanamarga.sushruta. Download the app to your cell phone or to your Android compatible tablet, and then you're off to the races. You can start using it. Once you've installed it, the first thing you do is you register. If you have any problems with registration, please contact support at jnanamarga.in. Support support at jnanamarga.in. Okay. Now, these lectures are intended to complement what you get from the app and the platform. The app comes integrated with the IIT PAL lectures. Okay, and these classes that you're going through, they link in with what you get out of the app itself. So the app integrates the NCERT book with the IIT PAL lectures, and this goes on top of that. Our flagship for JEE students is called Ramanujan for JEE, and it is now available for free download. So please try this if you're a JEE student. So you go to play.google.com and look for com.jnanamarga.ramanujan. Okay, and when you get Ramanujan, you will get maths, physics, chemistry, and you will get the formula sheets. And when you open the app, you will see a lot more. You will have the textbooks, you will have the slides, you will have the IIT PAL lectures, all integrated with in-context learning, which is what we specialize in. So now let me get on with the material for today. I've gone through this part of the material, right? The single resistive circuit, and we looked at the initial idea of AC source with conductance, AC source with resistance, and then we introduced this concept of a phasor diagram, right? Think of the phasor diagram as something that's rotating in along with time. So at t equals 0, in the circuit, the power is at some angle, right? You remember that the sine wave is now being converted into a circle, right? Sine waves and circles are synonymous, right? The angles, the cos of the angle omega t will give you the base, right? And so that is what drives this message, right? Now, if something is, say, a phase behind, that length will tell you, will correspond, the size of that amplitude will correspond to to this. Okay, so the the x coordinate will correspond with the with a switch in the phase. So when we say something is behind by a certain phase and we introduce this idea of a phasor diagram, what does it represent? Okay, so in a circuit, the various, particularly in an AC circuit, the voltage across various sources varies. Okay, it is still V equals IR and V equals with the impedance. We discussed impedance last time, right? But what happens is that the V and the I are a little different. Okay, so now that is, we're talking about the instantaneous V and the instantaneous I. And so when we think of, omega t, the driver going through, a particular, the voltage going through a particular, revolution in with respect to the phase, the current, and the it will lag and follow a slightly different phase. Okay, and the angle is will follow, it will follow behind or lead based on based on this, what is the actual phase. Okay, so that's how you should think of this. Okay, now the instantaneous power, as we discussed, V times I, right, in a purely inductive circuit, right? A purely inductive circuit lags behind, right? Now, because it lags behind, it is an Im sine omega t minus pi by 2, 90 degrees behind, right? Because it's a pure inductor. Okay. So now Vm times Im will give you the peak power, right? But what goes inside the peak power is cos omega t sine omega t. Therefore, it is sine 2 omega t, right? 1 by 2 sine 2 omega t, right? So multiply and divide by 2 here. Therefore, you end up with Vi by 2, which is the max power, and then sine 2 omega t, right? Because this can at most be 1, right? So the max power is Vi by 2, right? So now we can think of this as being a frictionless spring, similar to a frictionless spring. And the RMS power, instantaneous power, is like this, right? And the RMS power for inductive circuit, the average power is of course 0, right? But the RMS power is I square R, I RMS square R, right? So with a pure inductive resistive circuit, right? So for inductive circuit, it's one thing. For resistive circuit, it's another. Okay, that's the difference between an inductive circuit and resistive circuit, right? So now, what happens in the case of an inductor, like a pure inductor? The energy is absorbed from the power source and then it is returned back to the power source. Okay, that's what an inductor does. It during one half of the cycle, it's absorbing. It is like on a continuous basis, because it lags in phase. It's absorbing and returning power back to the energy source. And it's like, and that's what they mean by phase. So now we introduce this concept called reactance. XL equals omega L, right? And then finally we introduce this other term which we called impedance, right? And we then introduce the phasor diagram, right? So now a circuit with all three elements, and then finally we went on to discuss the circuit with all three elements in it, right? We then discussed the purely capacitive circuit, and then we said that in the case of the purely reactive circuit, the reactance is 1 over omega c, right? And therefore V over xc is I, right? Now V over xc is 1 over omega c, right? And therefore Im equals Vm times omega c, right? Now you would like, if you needed to understand this, right? What this phasor and this reactance terminology is doing, it's really taking what is a differential equation, right? And it is actually like linear differential equations, okay? and then they move it to another domain, which is called a transform domain, where these equations in that new domain, right, become these linear differential equations are dealt with almost as though they are algebraic equations. With resistance, you deal with only with algebraic equations, right? There's no dq by dt equals c dv by dt. There's no differential equation there, right? So now, when you do the same thing with AC circuits, you end up using these other elements, which are also, you know, linear. If you think of it from the point of view, when they speak of these elements, they do speak of these also as linear elements. These are very linear elements. They are linear, but in a way they are what you call, they don't have like a V equals IR kind of function, but in another domain they do have something like that. Okay, so and hence you have this, you know, when you introduce this reactance and finally impedance, you're taking what are differential equations and you're making algebraic equations from it. Okay, so that's the aim, the basic idea behind some of these tricks. Okay, so they are linear differential equations which in the so-called transform domain become more or less, you know, algebraic. You're dealing with these from an algebraic point of view. Okay, so this is, you know, it is very good to, if you choose to become an electrical engineer, this particular treatment of electrical circuits and electronics is will be essential, you know, and learning the why this is done is very critical. That's why, you know, I thought I should spend a little time, going over the ideas a little bit here, you know. And that's why, like, you know, when you eventually you will take a first course in linear systems, a first course in circuits, you know, and first course in circuits and systems, and then maybe a course in electronic circuits. Okay, electronic circuits have equivalents to things like inductors, etc., which are a little more sophisticated than that, you know. And they also deal with signals which they then amplify and rectify, you know. So and you will have a little bit of that material also when we go to modern physics a little bit, you know. You will see a little bit of it later, but first you must understand this part, you know, like what is an AC circuit. Okay, so in an AC circuit, what happens is that the capacitor is on the one hand charging and then discharging. There's a period of time when the capacitor is absorbing power, and then there's a period of time when it is discharging that power back to the AC source. Okay, so between t equals 0. So now if you look at this, right, the V of t, you just have a capacitor connected to an AC source. The V of t and the I of t are slightly 90 degrees out of phase, right? The I leads the V, right? And therefore, basically it is following the differential equation dq by dt equals c dv by dt. Q equals cv applies throughout the time, and when you differentiate dq by dt, it will become c dv by dt. Okay, assuming the capacitance stays constant, right? And therefore, dq by dt is I, and I equals c dv by dt. Now, when you have V purely sinusoidal, right, when the voltage source is purely sinusoidal, like what you will expect from a ideal power source, from a good power company, you will end up with, then you can, when you take the derivative of c dv by dt, you will end up with c omega vm cos omega t, right? So take the derivative of sine, you will end up with cos, and then you take the derivative of omega t, you will have one omega which then comes out. Okay, so now that c times omega is then coupled together and then brought to the other side, so that it is of the form V equals IR, and therefore 1 by omega C is the equivalent of resistance. Okay, so and then there is of course this idea of the phase, right? So then there is the resistance and then there's the phase. Okay, so keep that in mind. Okay, so once you keep that in mind, you end up with the omega C being like a in the reactance representing something like like what you see in a V equals IR kind of situation, right? Ohm's law, right? And so it lets you deal with these things in using algebraic equations. Okay, then there's this idea of the phase shift, right? So now at t equals 0 to t equals 4, the capacitor is charging. At t equals t by 4, right? When 1/4 of the cycle, the capacitor is fully charged and there is no current. Okay, so the derivative 0 becomes 0. The capacitor, C times dV by dt becomes 0, right? Because V peaks, right? Sinusoid V peaks. This hits 0, right? So during this phase, the area under the I versus T curve will give you the charge, right? So the area under the I versus T curve will give you the charge. So during this phase, it's been charging, right? Then the next phase, what's going to happen? The next phase, the capacitor is going to discharge. So what's it going to do? It's going to supply its charge back to the source. Okay, so there's this phase is called discharge. Okay, so that's how this works. Okay, so during the discharge phase, the I versus T is decreasing. The I versus T is negative and it's decreasing. Okay, although the voltage continues to be positive, the capacitor is returning it back. Okay, and then on the reverse side, again there is a situation where it's discharging while the V is negative, and then it is again charging. So it's a very different kind of thing. Okay, from T by 2 to 3T by 4, it's charging, but the current is then reversing. You see, it's charging, but then this is the plus and that is the minus. You see, plus and minus. During the second half, this is the plus and this is the minus, because the sine wave is now in the negative side. Okay, so the sine is going like this and then like this, like this and then like this, like this and then like this, right? So, and when it goes like this, the first half it charges, the second half it discharges. That's the action that goes on inside a capacitor when it's facing a AC source. Last time I also discussed what happens when it faces a DC source, right? So if you pay careful attention to what keeps going on, then slowly you will become very, very comfortable with this idea of how V equals IR is now being used in the context of a capacitor and an AC source. And the same thing, right? Remember that the inductor is just the alter ego of the capacitor. It follows the equation phi equals Li, right? Phi equals Li. So dq by d phi by dt equals EMF. Negative d phi by dt equals EMF, right? And therefore, what happens there? V equals L di by dt. That is a more traditional way. And in an electrical circuit, if L di by dt, this one is sine omega t, that one will be cos omega t. Okay, so that one will be lagging. Okay, so the current there will also be a sine wave. If you just put a inductor, the current will also be a sine wave. Only thing, it will be out of phase by it will be behind. It will start here, you know. So here the current starts there. In the inductor, it will start here and it will be going up, you know, and then it will be dropping and then it will be going down. It will still go one phase, but it will be 90 degrees behind. See, this is 90 degrees in front, this is 90 degrees behind. Okay, so that's what you need to understand. Okay, so what is the time lag between the voltage and the current? The time lag is a period by 4, t by 4, right? So it's a pi by 2, right? 2 pi is one period, pi by 2 is t by 4. One period is one full cycle, is 1/4 of a cycle, right? So it is good to understand, you know, what is happening inside the circuit and the in the math behind it, and that's what this picture was depicting. You know, you're of course welcome to go and see the full, and I strongly encourage you to see the full video in IIT PAL. You know, but my aim in presenting this is, you know, of course, to first encourage you to do that, and also to kind of present it in a simpler fashion. Okay? So now let's look at this, the voltage divider using capacitors. So what happens when you put two capacitors in series? You have VC1 equals IXC1, VC2 equals IXC2, right? And what is XC? 1 by omega C, right? XC1 is 1 by omega C1, XC2 is 1 by omega C2. So VC1 plus VC2 equals V, right? So that's how you solve these, you know, simple questions converted to an Ohm's law kind of situation, right? As I explained before. Okay. Now, from XC, we went to this. Now, let's look at the instantaneous power. What is the instantaneous power? V times I. P equals VI, right? V times I is always the instantaneous power. So now, we all know that the average power is 0, because when you integrate over one period, it's, you know, it like this, you know, it will, you know, multiply out to 0. IMVM by 2 sine 2 omega t integral 0 to capital T, right? My suggestion is, strong suggestion is for all of you to do the calculation. Go do the integral. Only then you yourselves will be convinced that it is 0. Now, what is the work done? The work done, or the energy, is half C Vm square sine square omega t. Okay, so that is the instantaneous power, instantaneous work, right? But the net power, 0 over a full cycle, right? There's no power being consumed by just a pure capacitive circuit in a AC, right? So first quarter of the cycle you see, and second quarter, etc., right? So notice that this one is, notice that this one is a slower wave, while the power is a quicker wave, because it is 2 omega t. V equals sine omega t, right? But the power is 2 omega t. Therefore, it is a faster moving wave. Okay. So half CV sine square omega t is, you know, and so sine omega t, cos omega t is actually sine 2 omega t, right? So that's how you end up with twice the frequency for the power, right? The energy released earlier is returned. So purely capacitive circuit, purely resistive circuit, there is no phase in a purely resistive circuit. Inductor lags behind, capacitor leads the voltage. Okay, and all these, this is the introduction of the LCR circuit. Okay, now the LCR circuit is essentially aimed at helping students understand this, you know, idea of, you know, phase diagrams and everything. Okay, now there are more complicated circuits than just the plain LCR, you know, LCR in series circuit. Okay, and there are many combinations of it also. I won't say more complicated, but many combinations of it. Now, but the pure LCR we will look at a little bit, but also the other circuits. Okay, now we then introduce this concept called the impedance. The impedance is the ratio of V of t by I of t, right? And what we are going to do is, in a circuit, we are going to introduce de Moivre's theorem. Okay. Now we write the power, right? V equals e to the power of I omega t. Okay. Now de Moivre's theorem says that e to the power of I t equals cos omega t plus I sine omega t, right? Or more simply, e to the power of I theta equals cos theta plus I sine theta, where I is the square root of -1, imaginary number, right? Right? So now e to the power of I theta equals cos theta plus I sine theta. So we then write it in this form, and then we do calculations in using this new definition. Okay. So then the Z, we introduce this term called impedance. Okay. Impedance has two parts. There is a resistive part which is real, and then there is a imaginary part which is either inductive or capacitive. Those two, they kind of have a little bit of a tussle. The inductor and the capacitor being one being a leader and the other being a laggard, right? So they kind of come together and then decide how this is to happen. Okay, so now we write Z as the impedance as a mix of the real resistance and the imaginary omega L and omega C. Okay, so and then these two are orthogonal to each other. The R is real, it is the X, and the XC and XL are in the Y or in the imaginary axis. So you can use I, or in some cases they use J instead of I. So we discussed all this last time. Okay? So then we introduce this concept of a LCR circuit. Now the LCR circuit most often is, just to keep things simple, is written basically connected with R, L, and C. Okay. Now based on how well the R and the L interact with each other, right? The R and the L could completely cancel out each other, which is a term which relates to this idea called resonance. We already looked at resonance in the context of simple harmonic motion. This is not too different actually. Okay, we introduced resonance in the context of simple harmonic motion, if you remember, and damping. These are all very in some ways allied concepts. Okay, so notice this is the LCR circuit written as a linear differential equation. V equals IR, which is the linear term, right? Which is the what is that, the non differential part of it, plus L di by dt plus Q by C, right? And Q is going to be written as 1 by C integral I dt. Okay. So what is Q? Q is integral I dt, right? So 1 by C integral I dt is the voltage across the capacitor. Okay. So 1 by C integral I dt, and Q is integral I dt, right? So you end up with, what if you differentiated it once more, you'll end up with a second order differential equation. Okay, and so what do you do with this? Okay, so what they typically do with this, but it's a linear differential equation. Okay, the terms are not complicated, they don't go against each other, and therefore to understand this, we then introduce this concept of impedance, and using impedance, a lot of it is converted, these differential equations then become linear algebraic equations, and that process is what we are doing here. Okay, so we define Z, and the modulus of Z is root of R square plus omega L minus 1 over omega C square. Notice that this is the real term and this is the imaginary term. So A square plus B square root of A square plus B square, right? So I equals V over Z. 1 over Z is that, right? So then I equals V over Z sine omega t plus phi. Okay. Now what is phi? Phi is related to is basically the phase, right? So tan phi equals omega L minus 1 over omega C by R. This picture, this picture, this picture, right? Tan phi is this divided by this. Tan theta is this divided by this, right? So using that, you can then write I equals V by Z sine omega t plus phi. Look at the V across R. What is the voltage across the resistor? Okay, the voltage across a resistor will be a band pass. Okay, so what does that mean, band pass? Okay, band pass is like there is a bandwidth, right? So there is a the power that that you see across the R, right? It is or the V that you see across the R will be of a particular frequency band. Okay, so what they do is they then switch the the system and look at it not so much from the time domain, but rather from the frequency domain. Okay, so there is a window delta W which is related to this term R by 2L. R by 2L is called the alpha of the circuit. Okay, now the delta W is the bandwidth. Okay, and that bandwidth represents the area over which the circuit has a high voltage. Okay, and therefore the delta W equals 2 times alpha, and alpha is R over 2L. Okay, so now the voltage across the resistance R in the LCR circuit is band pass. Okay, this is in the series LCR. Now there are so many other combinations you can have when you have a L, a C, and an R. You could make the C and the L in parallel, or you could make the L, R, and the L in parallel. Okay. Now, if your voltage, right, you kept increasing the frequency of the voltage, right? What happens, right? What happens to the resistor, right? So that is what this whole discussion is about. When they say band pass, low pass, there will be a range over which there is maximum voltage across the resistor. I keep increasing the frequency of the voltage, there will be a range of frequencies. When I say frequency, now I'm talking about omega, right? Angular frequency, right? Omega is related to the frequency of the sine wave, right? So there will be a range of there will be a range over which there will be maximum voltage absorbed across the resistor. And now, why does that help? Remember, this is kind of like a resistor, okay? And you want to maximally absorb that power. And how do you do that in the context of a particular circuit? Okay, so now there are so many different combinations between an L and a C and R, not just the single series combination. This combination will be a low pass. So at lower frequencies, there will be maximum power across RL. This combination is a high pass. When it's a high pass, at higher omegas, there will be maximum power across RL. Okay. Now this is the normal series one, which we just saw, right? The voltage across RL, in this case, this is the normal series one. This is the same as this one. Okay. Now in this case, it is a band pass. Okay. What does that mean? There will be a range of frequencies within which there will be maximum power across RL. Okay. Now here this is, and now which frequencies? Low pass means the frequency will be low. High pass means higher frequencies there will be maximum power. Band pass means there will be a band neither too high nor too low where the power across RL will be maximum. Okay, so that's how this RLC works. In the context of as a parallel band pass is a shunt across the line. This is also a band pass. This is also like this one, but it is a shunt based band pass. Okay. Now then there is this combination called a band stop, and this is known as a parallel band stop, series band stop and a parallel band stop. What does band stop mean? Band stop means that it will go up and then it will go up again, and the middle there will be a range of frequencies when there is no power. So it's the inverse of the band pass. The inverse of the band pass is the band stop. All right. So these are not so straightforward ideas, tricky ideas, but if you enter the field of electrical engineering, you will have to deal with some of these ideas. But typically they will have a first course in this also sometimes. But most often, you may not see it unless you take up electrical engineering much more seriously. But it is still taught. You may experience some questions in your NEET exam or JEE exam. You must know this material well. Okay. So now impedance consists of the R, then the XC and XL. Okay. So you have the Z. Okay. So now Vrms equals Irms times Z. V equals IR, as I explained to you. Z is impedance and is measured also in ohms. Okay. Remember the XC, right? We then write it 1 over I omega C, right? And XL equals I omega L, right? So remember those formulas, and then remember to learn to manipulate these almost like linear circuits, almost like resistive circuits. Okay, you write the capacitance like this and write the resistance like this. Okay, therefore using minus j by omega c for the capacitor and j omega L for the inductor. And then you do just do resistive circuit manipulation, and then you will end up with Z. And then you calculate the Z, and then you calculate V equals IR. Okay, this is how you solve examples involving circuits. Okay, then remember the material we discussed with respect to the bandwidth and then the phase. Okay, so so now these are the key ideas that go into this material. And therefore, let's look at this simple question. Okay, a series AC circuit containing an inductor and a capacitor and a resistor is driven by an AC source, okay, of 24 volts, 50 hertz. The energy dissipated in the circuit in 60 seconds is, okay, P average energy V squared by Z. Okay, what is V square? V square is what? 24 square, right? Now AC with 50 hertz, right? So 50 hertz is your omega. So XL equals 50 hertz is what? 2 pi times 50, right? Omega is what? 2 pi f, right? 2 pi times 50 will give you times 20 millihenry, right? 2 pi 50 times 20 times 10 to the power of minus 3 for the milli, right? So that will give you XL. XC is 1 over j omega c, right? And 1 over j omega c, therefore we'll end up with 26, right? So now you have to subtract one from the other, XC minus XL. So it is more capacitive than it is inductive. Okay, so 26.54 minus 6.28 will give you 20.26. Okay, so then you end up with 60 square plus 20 square, and take the root of that, you end up with 63 for Z. Then you do V square by Z. When you do V square by Z, you will end up with energy. Okay, so that's how this whole thing works. Okay, the case of a positive phase, difference comes from so now you have a different a circuit connected to an AC source EMF with T in seconds, gives a phase difference of pi by 4 between the EMF and current. So the following circuits will exhibit this. Okay, so now he's now talking about phase difference means the tan phi. So tan phi is 1 equals omega L minus 1 over omega C by R, right? This is the imaginary divided by the real, right? So omega L minus 1 over omega C must equal R. What is R? R is 1 kilo ohm in one case, right? C is something else, right? So in which case will it be the same? So I think, if you go calculate each of these cases, you find that only in one case, this case, that you find the R equals omega L minus 1 over omega C. Okay, so only in one case you find that. Okay, so in the other cases, it comes out to be something else. Okay, so so now, when you look at the power, as we said, we already looked at it in the context of power delivered, right? I square R, right? And so that gives you the average power, right? So this is how you solve all these problems. You look at it as though it is a you use pretty much Ohm's law. You use pretty much Kirchhoff's law. Only thing, you're now using Z instead of Z instead of just R, and then you have an AC circuit, and then you have an associated power. Okay, and therefore you have the VRMS. The VRMS is tied to the basically related to the average power. Okay, so so how do you calculate the average power? The average power is calculated using using these circuits. Okay, so what I'm going to do now is I'm going to try to wind this material down in the next class. But before we go into the next class, I'm going to give you a few ideas on what all you should do. Okay, you should solve a lot more examples with the AC circuits. Okay, so because it's not that difficult. Okay, it's not that difficult once you understand what all is going on. Okay, V square by Z, right? Cos phi is the average power. So you understand all these ideas. You read through. Maybe you take your NCERT textbook and read through it, or you use our app. Our app is the best way. You download our app, you read the material and look at the IIT PAL video. Read the material, look at the IIT PAL videos when you don't understand the material. Okay, and so when you do that, then you use the assessment, and then you solve some problems, and then look at the problems that we have in our slides. Okay, so that's how you go about it, and so the aim of the whole experience is to build your understanding around this AC circuits, so that you can solve problems dealing with bandwidth, problems dealing with power, and problems dealing with voltage and current. If you can deal with power, voltage, current, and bandwidth, and then the space, then pretty much that's all you need in terms of these examples. Okay, so spend a lot of time solving a lot of problems. Okay, so and now having given you that exercise, I will come back next class and do some more. I'm now going to spend a little more time also looking at briefly at what happens really in the context of the differential equation. Okay, so so let me come back to that material that I discussed, because sometimes it helps to do a second revision on some of this material, because it's not so easy, right? So this is the analytical solution. I already touched upon this before, right? So this is a simple LCR series circuit. Vm sin omega t equals L di by dt plus L IR plus Q by C, right? So now if you differentiate it one time, right, you end up with the second derivative for the I, right? Therefore, dq by dt is I, therefore you have 1 by C I, right, equals B cos omega t, right? So now, right, we rewrite this using Z, okay? So when you rewrite this using Z and a phase, you end up with this equation. Im times omega minus L omega plus 1 by omega C sin omega t plus phi plus R cos omega t equals Vm omega cos omega t. Okay. So now this is your Xc minus XL. This is your R. Okay. And this is your sin omega t and cos omega t. Okay. Therefore, this is why you're like, if you say that this side, this side is a particular phase, right? This side is phase dependent. This side is not, right? So from this, like if he introduces this tan theta, right? Tan theta as Xc minus XL over R, right? And therefore, he writes what's on the left side in terms of this. See, basically, you notice that this is like anytime you have sine of A plus cos of A, right? You then try to make it into a sine of A plus B. Okay. So sine A cos B plus cos A sine B is sine of A plus B, right? So that's what he's doing here. He is taking this part and he's taking this part and this whole remaining part, and he's trying to rewrite it in the form sine of A plus B. Okay. So when he does that, so he writes this as Im times Z times cos times omega t plus phi minus theta, and this theta is the tan inverse of Xc minus XL over R. Okay. So his aim is to rewrite this in the form of sine of A plus B. Okay. So when he rewrites this in the form of sine of A plus B, the omegas cancel, and then he ends up with Iz equals cos omega t cos omega t plus phi minus theta. Okay, that's how he ends up with I equals Vm by Z sin omega t plus phi. Okay, so now we come to this idea of resonance. We discussed resonance in the context of simple harmonic motion. Now we are discussing resonance in the context of an AC circuit. In the context of an AC circuit, resonance occurs when Xc equals XL. Okay, of a simple series AC circuit, resonance occurs in the context of when Xc equals XL. When Xc equals XL, you have a maximum power. Okay, and when does that occur? That occurs at that critical frequency omega equals square root of 1 over LC, right? When omega equals 1 over LC, you have this term going to 0. And when this term goes to 0, you then have this graph. Okay, as you change omega to be slightly different this way and slightly different this way, your current drops. Okay, so that's why we say that the voltage and the current across the resistor is band pass. This is an exact determination of band pass, and this is the Z. At this point, Z becomes the lowest. Remember, what is Z? Square root of R square plus Xc minus XL the whole square. When is this the lowest? This is the lowest when this is low, because this is a constant, right? So for some omega, this term goes to 0, and that is this critical frequency of resonance omega naught, right? And therefore there is a band around it, an alpha this side and an alpha this side, where we say that there is maximum power absorbed by the resistor. Therefore we say that's the band of the band pass. So it is omega this side and omega that side. That is the bandwidth measurement. So that's what we are talking of in terms of the band pass. Omega 2 minus omega 1, that width goes to explain your band pass. Okay. So this is, if you wanted a sharper resonance, you got to adjust the value of your R versus the L. Okay. So if you want, so adjusting that, so let's say you wanted that this like it to be very, very sharp. You don't want a nice flowing I versus omega, right? You want a very tight omega. I want maximum absorption in a particular band. Why would you want that? Well, let me explain to you, not in the context of AC circuits, but in the context of the radio, right? Radio, when you twiddle the knob, it is changing frequency, right? So now, within a small band, right, you want it to maximally absorb. I don't want, the neighboring radio station, or the sound from the neighboring radio station, noise from something else. I don't want all that. I just want the limited frequency, like a small band, hear it very well, and get the full signal from that little band. Okay, so that's why they have a narrow. So we try to narrow the bandwidth, right, so that you have a sharper resonance over a narrow bandwidth. So that is the bandwidth, and therefore you end up with these two terms: sharpness and quality factor. Okay, so now quality factor is omega naught divided by 2 times delta omega. Delta omega is related to this R by 2L. Okay, delta omega is related to the width of that band, right? Therefore, you want quality factor is omega naught by 2 times delta omega. Delta omega is R by 2L, right? So now you have sharpness, then you have quality factor. Okay, so in an LCR circuit, resonance frequency is this much, Q is 100. What is the RN? What happens if RN, L, and C? What would the Q be, right? So you then look at what happens to omega and what happens to delta omega. Omega naught by 2 delta omega, quality factor. Okay, so look at a couple of examples involving this as well: resonance frequency as well as resonance in the context of the AC circuit. So please spend some time understanding the material around resonance AC circuits, and then do some problems. Here's one more resonance question, but I will maybe do a quick look at this one before we continue with the discussion. There is more discussion with low power, high power, etc. In the next class. Okay, but please spend a lot of time looking at power and LC circuits, and finally we will then close it out next time. Okay, and then in terms of understanding the ideas around maybe oscillators, because these are all reused, time lag and radio tuner, power conservation, etc. But then before we go on to transformers, okay, so power conservation and then finally transformers. But so all this we will deal with next time. But I do want you to all catch up completely. Solve a lot of problems dealing with this AC circuits. Now that you've had all the material pretty much covered, so maybe you'll not be able to do a few problems with respect to some of the terminology with respect to the oscillator and all that. Okay? But most of this, rest of it, the basic ideas you've already got. Therefore, you should be trying to build comfort and capability solving some of the problems involved. So my advice to you is that you spend some time understanding, because they can ask various types of questions, learn all the terminology associated with LCR circuits. I've tried explaining some of the terminology, but not all of the terminology. So we will look at some of the other terminology next time, but then these terms I thought I should really try to explain it sufficiently well enough so that you see, when you see these terms, you're not like sight. You don't want that. It's not that difficult. AC circuits is not that difficult. You must understand it simply, but you must understand it well. You must understand the impedance domain, right? And what they are doing there, why they are doing that, and then you must understand all this frequency side discussions associated with band pass, low pass, high pass, okay? And at the same time, must also understand how to solve problems dealing with these AC circuits, okay? So much for this material. Next time we will continue with AC circuits. I didn't want to do too much too quickly, but then before that, I want to make sure that the students have spent some time solving some real problems. Okay, there is no point doing more and more problems if you're not going to be doing it. There's no point having just the teacher do problems. Always the students who do problems are the students who will face because you only have to face the exam. I cannot face the exam. So spend a lot of time attempting a lot of problems. All right. Okay. So let's end today. Then we will continue next week. I seriously implore all my students to download the app, register, and then commit themselves to spending time, not just with listening to the lecture, but also with spending a lot of time solving problems and doing their very best in building their own acumen in problem solving with these questions. Okay. Learn the material by listening to the IIT PAL lectures. If you don't get it from what I say, okay, I go a lot faster, okay, because there is a goal in going faster. Goal in going faster so that you can also read the textbook if you're not too impatient. But you must see the IIT PAL lectures to get the full detailed treatment, because they deal with it over 7-8 lectures. Okay, but this is to provide you that ongoing understanding, so then you can build the details understanding. Okay, so please understand how we use this the material, and what we provide and what IIT PAL provides, what the textbooks provide, what you will get from reading H.C. Verma. Okay, so this is the plan that we have for physics. There are no easy ways out. You want to get through NEET. There are million students taking it. You want to get through JEE. There are million students. You got to make the effort. You got to understand, and then it will stand you in good stead when you pass the exam. And what you have learned is always knowledge enriches you. And you will learn from that when you look at other things. If you choose to become an engineer, particularly, all these are very important. And then maybe even for the doctors, down the road, there's so much electronics in medicine, biomedical engineering, full of from everything from MRI to your sonar, acoustics, so there's so much that's done, like what happens in the signal that they use to for detection, so much material, so much electronics today is used in your field, so it helps to learn. Don't think this is only for people who study for engineering. No, you want to be a proper doctor. Let's say they make you a radiologist. Not everybody gets to be surgeon. You may end up radiologist. You may end up in other fields where you have to understand this. Maybe you have to understand the dialysis machine. You have to understand so many different things. All these things, they touch on the physics. They don't. You're not like going to manage with just davaya, right? No, it doesn't work. So please, even if you are planning to become a NEET student, pay a lot of attention. Pay attention to all parts of physics as well. Okay? Please do not think physics is less important if you're trying to become a doctor. It is the most important subject to do well in NEET. Believe me, not the most important. Do well in NEET, but it's the toughest subject in NEET. So because you have to be able to save time when you solve those problems, and you have to get through at least, if there are 45 questions, at least 35 you have to get in physics. With everybody struggles, flounders a little bit in physics. So, but 35 out of 45 you must get if you want to be successful in the NEET. That's why I emphasize, I teach it as well as I can, and we use IIT PAL for that reason. All right. See you next week.